All right, this is Module 29, Medians and Altitudes. Okay, so first thing I need to talk about is what a median actually is. And a median of a triangle, it's going to be a segment from a vertex to the midpoint of the opposite side. So we've had a few modules that have talked about finding midpoints and perpendicular bisectors. Medians is basically the same thing in finding that midpoint, but all you're doing with that midpoint is now connecting it to the vertex of the opposite side. So the medians of this particular triangle, ABC, are going to be BF, CD, and AE, because they go from the midpoint of one of the sides to the opposite vertex. The three medians of a triangle create the point of concurrency, and we're going to call this the centroid. And the centroid has specific properties. One of the properties is that it will always be inside the triangle. So we would label or call point O, in this case, the point of concurrency, is going to be our centroid. And this is kind of an interesting fact if you talk about centroid in physics, but centroid is the center of gravity for an actual triangle. So, all right, so we have a coordinate example we've talked a little bit about, but in this particular example it says find the coordinates of centroid C. And the reason this is kind of dating back way back to another module is because you have to use the midpoint to find out what the actual to find and construct the centroid with this coordinate proof. So we sketch RST, then we're going to find the midpoint M of RS and sketch the median TM. So when we do this, we have to first add the x values, then add the y values, and divide it by 2. We're basically taking the average, and when we do that, we find that the midpoint is going to be 2, 6. So when we plot 2, 6, you draw a line from that point, so this point here, 2, 6, we label it M, and you draw a line from M to the opposite vertex. So that would be angle T. Then we're going to find the midpoint of X of ST and then sketch the median of Rx. And we continue to do this throughout, and we find out that the centroid is actually going to occur at the point 3, 4. Because if we did the exact same thing with RT, the midpoint would be here. And it's a little bit easier to do this on a XY axis because you can find out just kind of using midpoint and drawing lines. So it's not too difficult of a construction. So we say median, centroid, and we found out our centroid is 3, 4, the point. So notice the distances from the vertices to the midpoints of the opposite sides. So the distances from the vertices to the midpoints of the opposite sides. Those are what are called your medians. Okay, so here is another picture of what medians create, and we have a theorem that is associated with the concurrency of these medians. And what happens, this is kind of an interesting thing. It's similar to mid-segment in that it's a mathematical or algebraic property, but the medians of a triangle are going to intersect at a point that's going to be 2/3 the distance from each vertex to the midpoint of their opposite side. Now, in terms of words, that's a little confusing for me. I like formulas. So if you take the entire length of, for example, I'm going to do AE. AE's entire length, and you multiply that by 2/3, that will give you the length from A to the centroid. And if you do that all throughout the triangle, that is a valid formula for each of the medians. So you have to remember 2/3 is associated with medians of a triangle or with centroid. So let's get some application with this. So I have this figure here. In triangle RST, I tell you that Q is the centroid. Again, when I said like in center or circumcenter, this is again one of those key words that you should say, oh, centroid. Automatically, I should think 2/3 when I see centroid. So they give me SQ's length is 8. I'm asked to find QW's length and the entire length of SW. So what I do is I apply the theorem. And the theorem states that if you have the entire length of SW and multiply it by 2/3, it will give you the length of SQ. So what do we know? We know SQ. So we plug in SQ, and then we have to solve for SW. Since we have a fraction here, we have to multiply by its reciprocal, 3/2, and we will get 12 is equal to SW. So if we know that SW's entire length is 12, that's one of the things that we were asked to find right here. The next thing we were asked to find is QW's length. Now, in terms of algebraically, this is pretty easy because if we know the entire length is 12, they give us a part of the length is 8. Well, that means that this length here is going to be 4 because you do 12 minus 8. So that's how we find QW. So in using this, in using the 2/3, you can find out the individual lengths for each one of the segments within the triangle that are created by the medians. Okay, so here's another example. There are 3 paths through a triangular park. Each path goes from the midpoint of one edge to the opposite corner, and the paths meet at point P. So, point P is a little hard to see, so I'm putting it right here. That's the points of concurrency. That's where the medians intersect. So, I tell you that SC is equal to 2,100 feet, and I'm asking you to find PS's length and PC's length. So, again, I gave you all of SC, so what you do is you basically set up the 2/3 formula. So we have 2/3, and you see the answer down there, so we should get that answer if we do everything correctly. 2/3 of SC's entire length is going to equal CP's length, okay, or PC's length. If I know SC is equal to 2,100, I just plug in 2,100. I substitute it, just kind of like we did in the last one. And here, if I do 2/3 of 2,100, that becomes 700. That means PC's length, or CP's length, is equal to 1,400. And that is feet. Go. So I know 1 here. The next thing I'm asked to find is, so this guy's good, we're asked to find PS's length. So if we know that CP's length is 1,400, we can say, okay, well, 1,400 plus some length is equal to 2,100. And this some length is PS's length. Okay, so you just solve algebraically and you should get 700. So we have 700 and 1,400 for PS and PC respectively. All right, next thing we have to talk about is altitudes and what an altitude is. This is actually very important when you're actually finding area of a triangle. You construct altitudes to find out what the height of the triangle is. So what is an altitude? An altitude of a triangle is going to be the perpendicular segment from a vertex to the opposite side or to the line that contains the opposite side. And that's kind of key here because in an obtuse triangle, you are going to have to extend, like this little part here is extended from the original side because you have to create a segment that's perpendicular. So these are called your altitudes. They measure the height of the actual triangle. Okay. When we construct all 3 altitudes, they intersect at a point of concurrency. So the lines containing the altitudes of the triangle, they're going to be concurrent, and we call this the orthocenter. And remember, altitudes are perpendicular, but they are not bisecting the opposite side. So this is a no of what I would do. This segment is not congruent to this segment. You can put something like that is fine, but do not mark these congruent like in perpendicular bisectors. Okay? So again, we call this the orthocenter, altitude's orthocenter, and P, we say P is the orthocenter. Okay, so different cases for orthocenter. This is again, one of the reasons why we have a lot of different cases for some of the other constructions that we've done. But we have in an acute triangle, orthocenter is going to be inside the triangle. We have a right triangle, the orthocenter is on the triangle. In an obtuse, the orthocenter is going to be outside the triangle, and you will see these in constructions. So this is one example here, acute triangle. We constructed all three of the altitudes, and they intersect inside the triangle. For a right triangle, the altitude is going to intersect on the right angle here, and then the obtuse triangle intersects somewhere outside of. And this becomes a little bit easier to visualize when you actually do a construction with these. Okay, so let's recap. We have the altitudes, angle bisectors, perpendicular bisectors, and medians. Angle bisectors create in-center, perpendicular bisectors create circumcenter, altitudes create the orthocenter, and medians create the centroid. There is a kind of fun mnemonic device that uses the first letters of each one of these so that you hopefully will not have a issue remembering these. Because I remember when I was learning these that I had a little bit of an issue and I got these very mixed up. So I'm going to go from top. I have all boys in, party, boys, club, are out, meeting, chicks. Angle bisector in-center, perpendicular bisector circumcenter, altitudes orthocenter, medians centroid. And they match up completely. Okay, next you have constructions. So we have to actually construct medians and centroid. And I actually split these up into a couple videos because these are, I think, some of the harder constructions. So we're going to do a median, centroid, altitude, special case altitude, and we're going to do orthocenter as well. So please refer to those videos now.